Okay, hi guys. My apologies, the main speaker is not here. My name is Michael Wong. I'm the CEO of OpenMP. So some of you guys may or may not know me. I've given talks on this subject before. I'm going to have Jim Cownie come in and talk with me about this because what I want to talk about today is the vector programming model in OpenMP. So for that, I'm going to skip past much of this talk because much of this talk was given at ACCU in Bristol. Okay, so and get to the part that talks about vector programming. All right.
Is this talk available?
It's probably available on ACCU, actually. It talks about a lot of different things, about accelerators, as well as the affinity models, and things like that. So I want to just focus for now on the vector model for now. All right.
Michael, could you step on that side?
Sure. Thank you. All right. All right, so now we're stepping through the affinities. All right, SIMD language extensions. All right. I don't know what was done for yesterday. Okay. All right. So let me just start right away in terms of the committee. It's led by Shinmin, whom we were trying to get here. There are a whole bunch of other people involved from various different companies. Much of the vector proposal came from what Intel already have had in their compiler for quite some time now. But other people that's been involved, as you can see, is a broad base of different companies between Oracle, IBM, BSC, okay? So I just wanted to share that just to make sure that I give credit to these slides because they're not actually my slides. So one of the things that you're going to find is what's the problem with SIMD language extensions, okay? It seems pretty clear that SIMD registers has been steadily increasing, and in fact, they're verging on 1024 fairly soon. The instructions are getting certainly more powerful and more complex. It's harder. It's becoming much more difficult for compiler to select the right instructions, and the code pattern that has to be recognized by the compiler is increasingly becoming more difficult. The precision requirements often essentially inhibit SIMD code generations. Ultimately, what I'm noticing is this, and I work in sorry, I'm just trying to remember. Okay, and I work in compilers. One of the great hope of compiler code generation, of course, is auto vectorization. That great hope is nearly over, because we're finding that it's very difficult for most code bases to auto-vectorize. I remember when I used to work on the cell, 70% of the time we spent was actually and that was the previous generation of accelerator processor, to actually vectorize instructions. And certainly these were some of the reasons as to why we think auto-vectorization is going to have difficulty. All of this essentially, and then there are other difficulties. What sort of loops can be vectorized? It turns out it's actually fairly complex. These loops have to be countable. They have to be single exit, single entry, straight line code. I mean, even if statements in there is problematic. Everything else they call have to be vectorizable potentially. You know, it can only address certain non-contiguous memory addresses, alignment difficulties, and things like that. This is just listing some of the fundamental difficulty of auto-vectorization, never mind you trying to vectorize it. So I think all of these is what's essentially driving the need for the industry to call for a better language support for SIMD support. And this is where we wanted to standardize a much more high-level way of describing SIMD. Instead of you having to always convert it depending on where the local platform happens to be, whether it's whether it's SSE, whether it's IBM's version is VMX, VQX, and the 20 possible variants that it has. A high-level language support gives you that ability, gives the compiler better opportunities to optimize it. Okay, so that's why OpenMP has taken the lead and probably the industry's first high-level vector language support. Okay, and this is what I'm just show you quickly a little bit of syntax here. You're familiar with most of this, right?
I can talk to some of
this.
Okay. I'm not.
Okay. I'm going to have Jim come in.
Disclaimers first, and then. Okay, you have a mic.
Ah.
I can just shout.
But you're recorded, so.
Oh, I'm recorded. Oh man. Well, as long as you don't ever, you wipe it somewhere. There, so that's okay? Okay. So a few disclaimers up front. I haven't seen these slides. I'm normally responsible for the runtime part of OpenMP, so I'm the architect for our runtime, which is also now the LLVM runtime. So it's open sourced under BSD license, you can get it. So mostly I ignore the SIMD stuff because the compiler does all that and I don't have to worry. However, since I'm here and the presenter who wasn't here, who now owes me at least one beer, and he's from Intel too, I will attempt to give these slides. So, as Michael said, we have a big problem, which is that all of these machines have these vector operations and the compilers aren't smart enough to, well, sorry, I get told off by the compiler guys when I say that. It is, in many cases, impossible for the compiler to deduce that it can vectorize a particular loop without being given a lot more information from the user about how the code is really being used. So in C, the classic examples are where you have two pointer arguments into a function and they may alias within the function. The compiler has to assume that that function would be called in a way where they could alias, unless you as the author of the code have told them more by putting restrict on the pointer arguments. There are other cases where the compiler needs similar information, and that's what these directives are. They are statements to the compiler so that you give it much more information which you knew but the compiler can't deduce and which it needs to ensure that it can vectorize the operation. They're also quite strong statements in as much as often the compiler, even if it can deduce that it could vectorize something, may not have enough knowledge to know whether that was actually worthwhile. So it may have to generate, so for instance, you have a function with a vector and a length. If the compiler doesn't know that the length is always greater than 1,000, say, it may decide that it's easier just to generate scalar code because the cost of setting up the vectors, and in particular making sure that the things are correctly aligned, because many of these vector instructions only work on aligned data, there's a large cost in entering a vector loop before you get to the point where you actually get the benefit of the vector operations. And therefore, passing more information into the subroutines to say this is going to be a nice long vector, or these arguments are well aligned, gives the compiler much more information. So what these OMP SIMD things do is they partially override some of the compiler's sanity checks, where it might have decided, well, I could vectorize this, but I really don't think it's worthwhile. When you put OMP SIMD on it, you're saying, hey, actually, believe me, I wrote this code. This is going to be worthwhile. Or at least, let me try this to see if it's worthwhile, and don't stop me trying it because you don't think it's worthwhile. So they're quite strong. They're not just hints. They're saying, do this. I'm asserting the correctness of your ability to do this. Therefore, they can break your code. If you put these in and the code doesn't obey the statements that you've made about it, so for instance, you say on one of the arguments, it's aligned, and then it turns out that it wasn't, you'll get a segmentation violation when you run the code. Well, fine. You know, we're doing this in C. C is a language where you shoot your foot off. That's what it's for. The safety catches are off. So a lot of operations that describe, a lot of clauses that describe how data is shared, how to bring it into the conceptual vector lanes that are going to be operating on the loop. As I said, I'm not an expert on all of these, but here we can see the aligned, the linear, the safe len that says, because we're vectorizing, there's a bit more restrictions that we can allow in the parallelism. If we say that a loop is parallel, we're allowing any possible sequence of iterations to occur. So it could execute all of the even ones, then all of the odd ones, or it could execute from the far end, or it could do anything. With the vectorization, we're saying that there are some cases where there can be a feedback and we're moving up the thing, but the feedback is at a sufficient length that we know that we can vectorize up to this length, whereas if we went further, then we would be loading data that we should have read an updated version of. We can parallelize, and so here we're oh, all right. So this is yeah, okay. So this is just a SIMD loop. Yeah, right. So this is a SIMD loop. Oh, this is parallelize and vectorize. Yeah, okay. So in the one directive, we can say this is a parallel loop and it's also a SIMD loop. So we want to chunk it into SIMD width pieces and then chunk those out in parallel.
This is a simulation. This is a simulation as to how it first parallelizes across different threads. Okay. Across different threads, and then it divides the vector, and then gives you the vectorization after that. Okay. And then now we have the SIMD function. There are certain functions you might actually want to actually generate vector code for. Okay. So.
Right. So the point here is that normally, if you make a function call inside your subroutine, inside your vector loop, sorry, then because of the standard, unless you can inline it, because of the standard calling conventions, the compiler it's got all this nice data sitting in a SIMD vector register, but it has to push it out into store so that then it can pass it, or into store and then move it into integer registers, because that's how the function calling convention works. That's clearly very costly. And so instead of that, to allow the compiler to, in effect, cheat on the calling conventions, there are some new vector calling conventions that allow the compiler to pass arguments into the subroutine in vector registers, so it doesn't have to spill them out to store and pass them through integer registers or pass pointers to them. And that's what this declare SIMD on the function says. This is a function that I want you to generate a version. So we're going to generate multiple versions of this. We're going to generate a version that takes vector arguments so they can be in SIMD registers and therefore improve the performance. These are similar, are they not, Michael? Yes. Right.
So it's just kind of flatten it and put it inline it.
It's not inlining. If it inlined, then it would be fine already, because it doesn't need to know this. This could be a function that had been compiled in a separately loaded library, right? Even so, you didn't even know anything about it. But the normal calling conventions, the standard ABI application binary interface calling conventions for all of these machines, don't allow you to pass registers in arguments in SIMD registers, right? So if you had data in a SIMD register that you want to pass to a subroutine through the standard ABI, you have to store it into memory, right? Admittedly, it'll end up in the cache, but it goes into memory. And then either you pass a pointer to it in the subroutine, or you load it even in some cases into integer registers to pass it to the subroutine, or into x87 floating registers or some, not on Michael's machines, some horrible way. So you had data right up near the processor in the vector registers. You just wanted to do some small number of operations on it. You don't know what they are at the time you're generating the outer vector loop, though. They're in a subroutine that you may not have seen the content of. So this allows you to use a different set of calling conventions. So it's not inlining, because inlining there wouldn't be a call at all. There wouldn't be a new stack frame. You wouldn't have branched off to the other library wherever it happens to be in store. The compiler would have done the whole thing. So it is different. Yeah?
The next one is talk about the in-branch functionality.
Okay, so this I'm really not familiar with, but I guess that it's to do with masking.
Yes.
Okay.
And I think that's basically it. That covers all the OpenMP vectorization features. Any questions?
What would a hardware guy have to do to merge this together? What would the hardware guys have to do?
What would hardware guys need to do to kind of support this on the hardware level?
So the question is, what would hardware guys have to do to support this on the hardware? I don't think that the hardware guys need to do anything more than they've already done. They've given us this interesting instruction set with wide vectors, and this is in the sense of that was someone asks you, how was your dessert? And you answer, well, it was very interesting, which means I didn't like it much, but I'm not prepared to say. So we have these interesting instruction sets, and we now are trying to generate a language that can program them. If you look, I only realized this recently, and once I realized it, it wasn't at all surprising, and I should have realized it long ago. But we write languages that target the machines we have, right? Certainly in HPC, we're not being very abstract. We don't go off and say, I really like applicative languages, pure languages, whatever. We go, what hardware did you give me? Well, I better make it possible for people to use that, right? So, we have MPI because we ran out of being able to build faster processors, faster nodes, and it's sort of obvious that you run out of time before you run out of money. So if you're going to build the fastest computer in the world, you spend a load of money on the fastest node you can, but you still got money left. So you buy 2 or 3 of them, or 4 of them, 1,000 of them, 100,000 of them. You connect them together, and then you need to program that, and we have MPI to do that. But MPI arose because those were the machines that were being built. It wasn't a case of we sat down and did MPI. I was on the MPI 1 standard committee. We didn't sit down and do MPI because we thought that's a great programming model. We did it because that's what the machines are like. And similarly here, we're catching up with the way that the hardware already is. So it's not a case of wanting different hardware, it's a case of catching up, letting you program the hardware you already bought. Is that okay?
So another way to think about it is I think each compiler for that particular hardware is going to generate the specific instructions that's going to be ideal for that hardware.
Specifically my question, so thinking about AVX, so AVX has hundreds of different instructions, so will the compiler be able to use the...
Yeah, so okay, so I'll answer that because you asked AVX. So the question was, AVX has a very large number of instructions. Can the compiler actually use them all? And my answer to that is that one of the reasons that AVX has so many instructions is precisely to enable the compiler to work. The thing that compilers find really hard is where you have something that you would expect to be a full matrix, this operand, that operand, filled in nicely. Then it's easy, right? Register, memory, whatever, register, register, register. That's easy if it's filled in. The cases that are hard for the compiler are where there are some bits missing, right? So you start trying to generate that instruction, you suddenly find that one of the operands is in a register when you needed it in memory, and now you have to generate some different instruction. So I admit I was shocked. I went when some of the fused multiply add instructions were announced, and I read a microprocessor report thing. This shows you how Intel works. I found out more about our new instruction set from microprocessor report than I'd known beforehand, and it says there are 327 new instructions for something, and then there are 249 different fused multiply add instructions, whatever it was. And you think, why do you need 249 fused? I'm sure 249 is wrong, but and then you think, well, okay, so fused multiply add is really a 4-operand instruction, except our instruction set encodes 3-operand instructions. So that gives you an issue of, which of the operands is destroyed, right? Then you've got add and subtract, right? And you multiply up all of these possibilities along with addressing modes and so on, and you get this huge number of instructions. But really, conceptually, it's just fuse, multiply, add, or subtract on every possibility of where things are living and so on. So the huge numbers of instructions aren't the complexity for the compiler. It's where you have a huge number of instructions but are missing a few critical ones that cause the compiler people real grief.
I think we have to end here.